March 15, 1945. Atsugi Naval Air Base, 40 kilometers southwest of Tokyo. Commander Takeshi Yamamoto stood inside a captured American B-29 Superfortress, the massive bomber that had been forced down intact during a raid on Yokohama 3 weeks prior. Around him, Japan's finest aeronautical engineers examined the aircraft with instruments and notebooks, cataloging every system, measuring every component, searching for the technological secrets that allowed America to darken Japanese skies with formations numbering in the hundreds. Yamamoto had graduated from Tokyo Imperial University in 1936, had studied aerodynamics in Germany, had contributed to the design of the Zero fighter that once dominated Pacific skies. He understood aircraft as sophisticated machines requiring precision manufacturing and meticulous maintenance. The B-29 represented American industrial capability at its apex, a bomber capable of flying 3,000 miles, carrying 4 tons of ordnance, operating at altitudes exceeding 30,000 feet. But what Yamamoto discovered inside that captured Superfortress contradicted everything he understood about proper aircraft engineering. Beneath inspection panels, securing critical systems, holding together components that should have required precision fasteners, he found improvised repairs, field modifications, solutions that looked like desperate expedients rather than engineering sophistication. He found maintenance that had been performed with wire, tape, and pragmatic disregard for theoretical perfection. Japanese aeronautical philosophy in 1945 represented the culmination of decades pursuing technical excellence through precision and perfectionism. The Imperial Japanese Navy's aircraft, the Zero fighter, the Betty bomber, the engineering that had allowed Japan to build the world's largest battleships, reflected a design culture that valued refinement, craftsmanship, and adherence to exacting specifications. Japanese aircraft were built in factories where tolerances were measured in fractions of millimeters, where components required precise fitting, where maintenance demanded trained specialists and proper tools. This philosophy produced remarkable aircraft. The Zero fighter, introduced in 1940, had been superior to every Allied fighter in the Pacific for the war's first 2 years. Longer range, better maneuverability, lighter construction that allowed performance advantages that American pilots initially could not counter. But the Zero's excellence came with inherent fragility. Its lightweight construction meant minimal armor and unprotected fuel tanks. Its precision engineering meant that field repairs required specialized parts and trained mechanics. Its performance advantages depended on meticulous maintenance that combat conditions made increasingly impossible. By 1945, Japan's aeronautical superiority had collapsed not primarily from design inadequacy, but from industrial attrition. American submarine campaigns had severed supply lines, making aluminum scarce and aviation fuel precious. Strategic bombing had destroyed factories and dispersed manufacturing to underground facilities, where precision production became impossible. The pool of trained mechanics and experienced pilots had been depleted through years of attrition warfare that consumed expertise faster than training could replace it. But Japanese engineers, examining captured American aircraft, expected to find sophistication matching their own, precision manufacturing, exacting tolerances, systems requiring specialized maintenance. They anticipated that American technological superiority came from better engineering, more advanced materials, superior design philosophy. The alternative, that America won through crude pragmatism and overwhelming production, was intellectually unacceptable to men who had devoted careers to pursuing technical perfection. Commander Yamamoto led a team of 12 engineers, all graduates of Japan's finest technical universities, all experienced in aircraft design and manufacturing. Their assignment was explicit: reverse engineer American technology, identify vulnerabilities, determine if captured systems could be adapted for Japanese use. The investigation proceeded methodically, measuring airframe dimensions, analyzing metallurgy, examining engine systems, testing control mechanisms. The engineers documented everything in notebooks that would survive Japan's defeat, that would eventually reside in Allied intelligence archives, that recorded not just technical specifications but growing bewilderment, because the more thoroughly they examined American aircraft, the more they encountered engineering philosophy that contradicted everything their education had taught them about proper design. The first anomaly appeared in the B-29's electrical system. Japanese aircraft used carefully routed wiring harnesses, secured with proper clamps and protective conduits, installed according to engineering drawings that specified exact positions and fastening methods. The B-29's electrical systems followed similar principles, in theory. But throughout the aircraft, the Japanese engineers found deviations, wiring secured with improvised clamps, connections wrapped in standard electrical tape rather than proper insulation sleeves, repairs that had obviously been performed under field conditions using whatever materials were available. Lieutenant Kenji Sato, an electrical engineering specialist from Mitsubishi Heavy Industries, traced a control circuit that had been repaired mid-flight. The original wiring had apparently failed, and some American crew member had bypassed the damaged section using wire scavenged from another system, securing it with electrical tape and routing it outside the proper conduits. The repair violated every principle of proper aircraft electrical system maintenance. It was crude, improvised, theoretically unreliable, but it worked perfectly. The circuit tested functional, showing proper voltage and no signal degradation. The improvised repair had survived subsequent missions. The maintenance logs recovered with the aircraft documented 4 more combat sorties after the field repair was made. An American crew member, probably not even an electrical specialist, had fixed a critical system using materials at hand and knowledge gained from practical experience rather than formal training. This should not function reliably, Sato told Yamamoto, gesturing at the improvised wiring. The connection is inadequate. The routing creates potential interference. The securing method will fail under sustained vibration. And yet, he consulted the maintenance logs again. This aircraft flew from Saipan to Tokyo 4 times after this repair was made, under combat conditions. At operational altitude, it worked. Yamamoto examined the repair himself, turning the wire in his hands, feeling the crude simplicity that his training told him was insufficient. Japanese maintenance protocols required that any electrical system failure be addressed with proper replacement parts, installed according to specification, tested before return to service. Field expedient repairs were temporary measures only, to be corrected as soon as proper facilities and parts became available. But American forces, fighting across the Pacific with supply lines stretching thousands of miles, apparently accepted field expedient repairs as permanent solutions. They trusted crew members to improvise, permitted deviations from specifications, and somehow maintained operational capability, despite maintenance practices that Japanese engineering philosophy considered fundamentally unreliable. The implications were disturbing. Perhaps precision was not actually necessary for reliability. The hydraulic systems revealed the pattern more comprehensively. The B-29 used hydraulic pressure to operate landing gear, bomb bay doors, and turret systems, complex mechanisms requiring precise pressure regulation and leak-free connections. Japanese aircraft employed similar hydraulic systems, manufactured to exacting tolerances where fittings required proper torque specifications and seals needed exact dimensions. Hydraulic system maintenance in Imperial Navy aircraft demanded specialized training. Improper installation could cause catastrophic failures. Leaking hydraulic fluid could catch fire. Loss of pressure could render controls inoperable. The captured B-29's hydraulic systems showed evidence of multiple field repairs. Fittings had been replaced with parts that were close but not exact matches, different manufacturers, slightly different thread specifications, secured with additional sealant to compensate for imperfect fit. One hydraulic line had been repaired by cutting out a damaged section and splicing in replacement tubing, using compression fittings and safety wire, a repair that Japanese protocols would classify as temporary pending complete line replacement. But the maintenance logs indicated that temporary repair had remained in service for 8 months and 43 combat missions. The American maintenance philosophy apparently accepted that good enough was actually good enough, that systems didn't require perfection to function reliably, that field expedient repairs could provide long-term solutions, that crew members could be trusted to maintain complex systems without requiring engineering-level understanding. Chief Engineer Hiroshi Tanaka, who had worked on hydraulic systems for Kawanishi flying boats, spent 2 days testing every hydraulic circuit in the captured B-29. He documented pressures, checked for leaks, operated every system through full range of motion. Everything functioned within specifications. The improvised repairs, the non-standard parts, the field modifications, all worked reliably, despite violating proper engineering practices. "I don't understand," Tanaka admitted to Yamamoto. "These repairs are crude, The maintenance is careless. Parts are mixed from different manufacturers with different specifications. By every principle I was taught, these systems should fail. The hydraulic pressure should be inconsistent. The non-standard fittings should leak. The improvised splices should rupture under operational stress. Yamamoto looked at the test data, the maintenance logs, the evidence that contradicted theory. And yet this aircraft flew from Saipan to Tokyo repeatedly, carried its bomb load, operated its defensive armament, returned safely despite maintenance that we would consider inadequate. Yes, Commander, the Americans maintain operational capability through methods that should not work. I cannot explain it. The engine maintenance records provided the most comprehensive documentation of American field maintenance philosophy. The B-29's Wright R-3350 engines were complex 18-cylinder radial engines, each producing 2,200 horsepower through precision engineering that required meticulous maintenance. Japanese engineers examining the captured aircraft expected engine maintenance logs showing careful attention, specialized procedures, adherence to manufacturer specifications. Instead, they found documentation of pragmatic improvisation. Spark plugs replaced with alternative models when specified parts were unavailable. Engine timing adjusted using field procedures rather than specialized equipment. Cylinder head repairs performed shipboard using portable tools. Oil system modifications made to accommodate different lubricant grades when specified fluids were unavailable. The maintenance logs recorded these deviations matter-of-factly, without the apologetic tone that Japanese maintenance reports used when documenting any departure from proper procedure. Lieutenant Commander Yoshiro Nakamura, who had designed engine systems for Nakajima aircraft, studied the maintenance logs with growing cognitive dissonance. These engines should not achieve reliable operation with this maintenance approach, he told the engineering team. The Americans are using non-specified spark plugs, adjusting timing without proper instruments, mixing different oil grades. This is not proper engine maintenance. This is improvisation that should result in reduced performance and premature failure. But the flight logs contradicted that assessment. The captured B-29 had accumulated 847 flight hours since its last major engine overhaul, well within expected operational lifespan, but achieved through maintenance practices that Japanese doctrine would never permit. The engines had been serviced at forward bases in the Marianas, on ships, at hastily constructed airfields, by maintenance crews who apparently lacked access to proper tools and specified parts, but maintained operational readiness anyway. Yamamoto requested additional documentation from intelligence services, maintenance records from other captured American aircraft, interrogation reports from American POWs who had served as aircraft mechanics, any information that might explain the contradiction between American maintenance practices and aircraft reliability. The documentation that arrived over subsequent weeks painted a consistent picture. American military maintenance philosophy emphasized keeping equipment operational using whatever means necessary, trusted crew-level personnel to make pragmatic decisions, and accepted field expedient solutions as legitimate rather than inadequate. The Japanese engineers struggled to reconcile this with their understanding of how complex machinery worked. Precision engineering required precision maintenance. This was axiomatic, fundamental, the basis of their entire professional training. American practices violated these axioms and somehow achieved equivalent or superior operational readiness. The cognitive dissonance was profound. Either their engineering education was fundamentally wrong, or American success came from factors other than technical sophistication. The structural repairs revealed the philosophical divide most starkly. Japanese aircraft structures used stressed aluminum skin requiring precise riveting patterns. Each rivet had specified diameter, spacing, and installation procedures. Structural repairs required new skin panels fabricated to exact dimensions, riveted according to engineering drawings, and tested to ensure structural integrity maintained design specifications. The process demanded specialized facilities, trained structural mechanics, and proper materials. The B-29's fuselage showed evidence of combat damage that had been repaired in the field. A section of lower fuselage skin, damaged by anti-aircraft fire during a previous mission, had been patched using a sheet of aluminum cut to approximate size, secured with rivets that were close but not exact matches to original specifications, and reinforced with additional support brackets fabricated from scrap material. The repair was clearly visible, making no attempt to restore original aerodynamic smoothness or appearance. Japanese structural engineers examined the repair with instruments, measuring stress distributions and testing structural integrity. The repair was crude, used non-standard materials, violated proper riveting patterns, and created aerodynamic drag. It was exactly the kind of field expedient that Japanese maintenance protocols classified as emergency only, requiring replacement with proper repair at the first opportunity. But American maintenance logs indicated no intention to replace the field repair with proper work. The repair was documented, marked as complete, and the aircraft returned to combat operations. Subsequent missions showed no structural problems. The crude patch held, the improvised brackets supported loads, the non-standard rivets maintained structural integrity. The Americans had apparently determined that good enough to fly was the actual standard, not restored to original specifications. Captain Masaru Ishikawa, a structures specialist who had worked on the G4M bomber's lightweight airframe design, vocalized the team's growing realization: the Americans do not pursue perfection. They pursue sufficiency. Their maintenance philosophy accepts that field repairs, performed with available materials by crew-level personnel, can provide adequate structural integrity for continued operations. They do not require specialized facilities or engineering oversight for repairs that we would never permit outside of proper manufacturing environments. Yamamoto nodded slowly, because they prioritize operational availability over technical correctness. A bomber that can fly with a crude patch is more valuable than a bomber waiting for proper repair materials and specialized facilities. Yes, Commander, but it contradicts everything we understand about proper engineering. Their approach should result in higher failure rates, increased structural problems, reduced operational reliability. And yet their bombers fill our skies daily, while ours sit grounded waiting for parts that will never arrive. The most psychologically disturbing discovery came when examining the B-29's defensive armament systems. The aircraft mounted 1050 caliber machine guns in remote-controlled turrets, a sophisticated system using analog computers to calculate lead angles and coordinate fire. Japanese engineers expected this fire control system to represent cutting-edge technology, the kind of precision engineering that explained American success. The fire control computers were indeed sophisticated, analog computing mechanisms using mechanical integration to solve ballistic equations in real time. But the maintenance of these complex systems followed the same pragmatic pattern observed elsewhere. Connections had been reinforced with safety wire. Mechanical linkages showed evidence of field adjustment using simple tools. Replacement parts included components from different manufacturers with slightly different specifications, made compatible through improvised adaptation. Most tellingly, the instruction manual for the fire control system was written for crew-level personnel, assuming no specialized engineering knowledge. The troubleshooting procedures described simple tests using basic tools, with repair instructions that emphasized, if this doesn't work, try this pragmatism, rather than theoretical understanding of system operation. The manual assumed that maintenance would be performed by young men with minimal training, under field conditions, using whatever tools and parts were available. Lieutenant Takashi Suzuki, who had designed fire control systems for Japanese naval artillery, read the American maintenance manual with growing disbelief. This manual treats the fire control computer as a device that crew members can maintain and repair without engineering understanding. It provides cookbook procedures assuming the user doesn't understand the underlying principles. He searched for words. This is like giving a complex mathematical problem to someone who has never studied mathematics and telling them to just follow the steps. And it works, Yamamoto observed quietly. Their fire control systems maintained operational capability throughout this aircraft's service life, maintained by crew members following simple procedures without requiring theoretical understanding. The implications settled over the engineering team like a weight. American military equipment was designed assuming that maintenance would be performed by minimally trained personnel under adverse conditions using improvised methods. The equipment was intentionally over-engineered in critical areas, under-engineered in non-critical areas, and designed with sufficient tolerance that field expedient repairs would provide adequate functionality. Precision was sacrificed for maintainability. Theoretical perfection was abandoned in favor of practical sufficiency. Japanese equipment, by contrast, assumed proper facilities, trained specialists, access to specified parts, and adherence to engineering procedures. When those assumptions failed, as they inevitably did in sustained combat, Japanese equipment became impossible to maintain. American equipment, designed from the beginning to accommodate improvisation, continued functioning. Commander Yamamoto compiled his team's findings into a report that would eventually reach the Imperial Navy's Technical Command, though by April 1945, strategic intelligence mattered less than immediate survival as American forces approached the home islands. The report's conclusions were presented with the careful neutrality of engineers documenting observations, but the implications were devastating to Japanese military-industrial assumptions. American aeronautical engineering prioritizes operational availability over technical sophistication, Yamamoto wrote. Their aircraft are designed to be maintained by crew-level personnel, using improvised methods and non-standard parts. This design philosophy accepts reduced theoretical performance in exchange for sustained operational capability under adverse conditions. Japanese aircraft, designed to exacting specifications requiring precision maintenance, achieve superior performance when properly maintained, but become non-operational when maintenance conditions are suboptimal. The report included photographs of American field repairs, copies of maintenance procedures written for minimally trained personnel, and analysis of how American design philosophy differed fundamentally from Japanese approaches. But the most significant conclusion was strategic rather than technical. American industrial superiority derives not from more advanced technology, but from design philosophy that accepts imperfection and empowers low-level personnel to maintain operational capability through improvisation. This approach cannot be replicated through reverse engineering captured equipment, as it requires fundamental revision of our manufacturing philosophy and maintenance culture. The engineering team documented specific examples where American pragmatism achieved results that Japanese precision could not. The B-29's auxiliary power unit, a small engine used to start main engines and power electrical systems, was designed so that any mechanically inclined crew member could perform basic maintenance without specialized training. Japanese aircraft used similar auxiliary systems, but maintenance required trained specialists and proper facilities. American bombers could be maintained at forward airfields using whatever personnel were available. Japanese aircraft required rear area facilities with specialized capability. The Americans had created an industrial military system where equipment reliability came from design simplicity and maintenance flexibility, rather than manufacturing precision and engineering sophistication. They had recognized, perhaps intuitively rather than explicitly, that in sustained global warfare, the ability to keep equipment operational under adverse conditions mattered more than achieving theoretical performance under optimal conditions. For Japanese engineers trained to pursue technical excellence through precision and refinement, this realization was professionally humbling. Their education, their expertise, their entire approach to aeronautical engineering had been optimized for peacetime conditions where proper facilities and trained specialists were available. American engineers had designed for war, for chaos, for improvisation, for maintainability by scared young men using wire and tape and pragmatic disregard for theoretical correctness. The report generated bitter debates within what remained of Japan's aeronautical technical community. In spring 1945, senior engineers, men who had devoted careers to pursuing technical perfection, resisted conclusions that implied their entire professional philosophy had been strategically misguided. The suggestion that crude American pragmatism was superior to refined Japanese precision felt like intellectual betrayal, like abandoning professional standards that had been cultivated through decades of careful work. But younger engineers, especially those who had served at forward bases and witnessed the maintenance challenges that combat imposed, recognized the truth in Yamamoto's analysis. They had watched Zero fighters sit grounded waiting for specified replacement parts that never arrived, while American aircraft continued operating with improvised repairs. They had seen Japanese bombers require multi-day maintenance procedures in proper facilities, while American bombers received field maintenance and returned to operations within hours. The philosophical divide reflected generational and experiential differences. Senior engineers had been educated in an era when Japanese industry was pursuing technological parity with Western powers, when precision manufacturing and exacting specifications represented progress and modernity. They had built their careers on the assumption that technical excellence came from refinement, from eliminating imperfection, from achieving specifications that demonstrated mastery of engineering principles. Younger engineers, shaped by years of combat operations, understood that war revealed the gap between theoretical performance and practical effectiveness. An aircraft that achieved superior performance under optimal conditions but required specialized maintenance was less valuable than an aircraft with adequate performance that could be maintained under any conditions. Precision was useless if it could not be sustained in the field. Sophistication was counterproductive if it demanded resources that no longer existed. By April 1945, these debates were academic. American firebombing had destroyed much of Japan's industrial capacity. The planned invasion of the home islands would occur in environments where sophisticated equipment and precision maintenance were impossible. The imperial military was preparing to fight with whatever remained operational, maintained by whoever remained alive, using whatever materials could be scavenged. In this context, American maintenance philosophy, improvise with available materials, trust crew-level personnel to make pragmatic decisions, accept field expedient repairs as permanent solutions, was revealed not as crude necessity, but as strategic wisdom. The Americans had designed their military-industrial system for sustained global warfare under worst-case conditions. Japanese systems, optimized for shorter conflicts and optimal maintenance conditions, collapsed when those assumptions failed. Commander Yamamoto understood that his report documented not just technical differences, but cultural philosophical divides that explained why Japan was losing the war. In the final months before Japan's surrender, Commander Yamamoto's engineering team examined additional captured American aircraft: P-51 Mustangs, F-6F Hellcats, B-24 Liberators. Every aircraft revealed the same pattern: design philosophy prioritizing maintainability over sophistication, field repair capability over manufacturing precision, operational availability over theoretical performance. The Americans had created an aeronautical industrial system optimized for sustained warfare at global scale, assuming that equipment would be maintained under adverse conditions by minimally trained personnel using improvised methods. The implications extended beyond aircraft engineering to broader questions about industrial organization and military culture. American military forces apparently trusted enlisted personnel, teenagers and young men with minimal technical education, to maintain complex equipment and make pragmatic decisions about operational readiness. Japanese military culture concentrated technical authority and specialized personnel with formal training, reflecting broader cultural patterns about expertise, hierarchy, and trust. American maintenance manuals were written assuming users had limited technical knowledge but possessed common sense and mechanical aptitude. Japanese manuals assumed formal technical education and adherence to specified procedures. American design philosophy incorporated redundancy and tolerance, assuming that some components would be maintained imperfectly, but that overall system reliability would remain adequate. Japanese design pursued efficiency and precision, assuming proper maintenance and specified parts would always be available. These differences were not primarily about technology or manufacturing capability. Japan had demonstrated ability to produce sophisticated aircraft and precision manufacturing. The differences were philosophical and cultural, reflecting assumptions about how military equipment would be used, who would maintain it, and what conditions would prevail during sustained combat operations. Lieutenant Suzuki, reflecting on months examining American equipment, articulated the realization that haunted the engineering team. We designed aircraft for engineers to maintain. The Americans designed aircraft for crew members to keep operational. We pursued theoretical perfection. They pursued practical sufficiency. We assumed proper facilities and trained specialists would be available. They assumed only wire, tape, and improvisation would be available. Our assumptions were reasonable for peacetime or short conflicts. Theirs were correct for sustained global warfare. Yamamoto included these reflections in supplementary reports that he knew would likely never be read by decision-makers who could have acted on them. By June 1945, Japan's position was hopeless, not primarily because American technology was superior, but because American industrial military systems had been designed from the beginning to sustain global warfare under worst-case conditions, while Japanese systems had been optimized for assumptions that combat reality had shattered. August 1945, the atomic bombings of Hiroshima and Nagasaki, followed by Soviet declaration of war, ended Japan's capacity to continue fighting. Commander Yamamoto, standing amid the ruins of Atsugi Naval Air Base as American occupation forces arrived, reflected on the captured B-29 that had initiated his investigation 5 months earlier. The aircraft still sat in its hangar, now a museum piece documenting technological philosophical differences that had contributed to Japan's defeat. American occupation engineers arriving to assess Japanese aeronautical capabilities were surprised to discover the detailed analysis that Yamamoto's team had produced. They read the reports documenting field repairs, improvised maintenance, pragmatic design philosophy, reading descriptions of their own equipment written from an outside perspective that revealed assumptions they had never explicitly articulated. Captain Robert Henderson, a U.S. Army Air Forces engineer assigned to occupation duties, discussed Yamamoto's reports with their author through interpreters. "You understood our maintenance philosophy better than we understood it ourselves," Henderson observed. "We never explicitly decided to design for field repair capability using improvised methods. It just emerged naturally from our industrial culture and the practical requirements of operating globally." Yamamoto, speaking through the interpreter, responded carefully, "Your culture trusts individual initiative and pragmatic problem-solving. Your industrial system produces equipment designed for users rather than specialists." These cultural patterns translated into design philosophy that proved strategically advantageous for sustained warfare. Japanese culture emphasizes specialized expertise and proper procedures, which translated into equipment requiring conditions that combat made impossible to maintain. The conversation between engineers who had recently been enemies revealed that neither side had explicitly recognized the cultural technical patterns that influenced outcomes. American pragmatism had emerged organically from industrial culture that valued practical effectiveness over theoretical perfection, from military culture that trusted enlisted personnel with significant responsibility, from economic systems that prioritized mass production over precision manufacturing. Japanese precision had emerged from cultural values emphasizing mastery through refinement, from educational systems that concentrated technical authority in credentialed experts, from industrial traditions that demonstrated modernity through manufacturing sophistication. Neither approach was inherently superior in abstract terms, but for the specific requirements of sustained global industrial warfare, fought across vast distances under chaotic conditions, American pragmatism proved more effective than Japanese precision. Equipment that could be maintained with wire and tape by scared 19-year-olds using whatever materials were available outperformed equipment requiring proper facilities and trained specialists who no longer existed in sufficient numbers. The lesson was humbling for engineers on both sides. Strategic outcomes often depend less on technical sophistication than on how well design philosophy matches operational reality. In the decades following World War II, Commander Yamamoto's reports became foundational documents in studies of military-industrial effectiveness and design philosophy. American defense analysts, retrospectively examining why U.S. equipment had proven so effective across diverse combat environments, discovered insights and analyses that Japanese engineers had produced while trying to understand their own defeat. The reports documented assumptions that American designers had followed intuitively, but never articulated explicitly. The wire and tape philosophy that had bewildered Japanese engineers became explicit American design doctrine in subsequent decades. Military equipment specifications began formally requiring that maintenance be performable by crew-level personnel using improvised methods and non-standard parts. Reliability engineering incorporated assumptions about suboptimal maintenance conditions and field-expedient repairs. Training programs emphasized practical problem-solving over theoretical knowledge, trusting young personnel with limited formal education to maintain sophisticated equipment through pragmatic improvisation. Japanese aeronautical industry, rebuilding after the war, initially attempted to replicate American pragmatism by copying design features and maintenance procedures. But the deeper lesson was that design philosophy emerged from cultural patterns that could not be simply copied. American pragmatism reflected cultural values about individual initiative, trust in non-expert personnel, acceptance of imperfection, and prioritization of practical effectiveness over theoretical correctness. These values were embedded throughout American industrial and military systems, not just in specific design features. Post-war Japanese industry eventually found a different synthesis, combining traditional precision manufacturing with improved maintainability, creating products that achieved both sophistication and reliability. Sony, Toyota, Honda, and other companies that became globally dominant in consumer products applied lessons about design for maintainability while retaining cultural values about quality and refinement. The result was equipment that worked reliably, not because it could be repaired with wire and tape, but because it was designed well enough that field-expedient repairs were rarely necessary. Commander Yamamoto, who lived until 1989, witnessed Japan's post-war industrial transformation and the ironic reversal where Japanese consumer products became synonymous with reliability that American products sometimes lacked. In interviews conducted in the 1980s, he reflected on the war's lessons with the perspective of 4 decades. We learned that precision without maintainability is useless in warfare. America learned that pragmatism without quality creates long-term competitive disadvantage. Both nations evolved beyond their wartime philosophies, incorporating lessons from each other while retaining core cultural values. The captured B-29 that I examined in 1945 taught me that cultural assumptions shape technological outcomes in ways that engineers rarely recognize while living within those assumptions. The revelation that emerged from Japanese engineering analysis of American aircraft was not primarily about technology, but about the relationship between design philosophy and operational reality. American aeronautical engineers had created equipment that worked reliably, not because it was more sophisticated than Japanese equivalents, but because it was designed from the beginning to accommodate the chaos, improvisation, and suboptimal conditions that sustained warfare inevitably imposed. The stupid repairs that bewildered Japanese engineers, the wire and tape, the improvised parts, the field-expedient solutions, the maintenance performed by crew-level personnel without specialized training, were not crude necessities but strategic advantages. They represented design philosophy that recognized human and logistical limitations, that accepted imperfection as inevitable, that trusted young men with minimal training to solve problems pragmatically, rather than requiring them to follow procedures that assumed optimal conditions. Japanese precision engineering, pursued with dedication and sophistication by brilliant engineers educated in the finest technical universities, had been optimized for assumptions that combat reality violated. Equipment requiring proper facilities and trained specialists and specified parts might achieve superior theoretical performance, but sustained warfare destroyed facilities, killed specialists, and severed supply lines. The precision that Japanese engineers had cultivated as professional virtue became strategic vulnerability when conditions made precision maintenance impossible. The captured B-29 with its improvised repairs documented a fundamental truth about industrial warfare, that reliability under worst-case conditions matters more than performance under optimal conditions. That equipment maintainable with wire and tape defeats equipment requiring precision tools and specialized knowledge. That design philosophy, accommodating human limitations and chaotic reality, outperforms design philosophy, assuming orderly conditions and expert maintenance. Commander Yamamoto, standing in the ruins of his nation's defeat, understood that the lesson extended beyond aircraft engineering to broader questions about how societies organize technological capability. Democratic industrial systems that trusted individual initiative and pragmatic problem-solving, that designed for users rather than experts, that accepted imperfection as inevitable, these systems proved more resilient than authoritarian systems that concentrated technical authority in elite specialists and assumed conditions would remain within designed parameters. The Americans had fixed critical systems with wire and tape, not because they lacked sophistication, but because they understood that in war, the side whose equipment keeps working despite chaos and improvisation and scared teenagers performing maintenance without proper training, that side achieves operational availability that theoretical superiority cannot match. The revelation was technical, philosophical, and ultimately strategic. Pragmatism defeats perfectionism when reality refuses to cooperate with theoretical assumptions. Commander Takeshi Yamamoto died in 1989, having witnessed Japan's transformation from defeated empire to economic superpower, having seen Japanese manufacturing philosophy evolve to synthesize precision with reliability, having lived long enough to recognize that the war's lessons about design philosophy and cultural assumptions had applications far beyond military equipment. His reports analyzing captured American aircraft, written in spring 1945 amid national collapse, became historical documents studied by engineers, military analysts, and scholars, examining the relationship between technology and culture. The captured B-29 that initiated his investigation survived the war, was eventually returned to American control, and now resides in a museum where it serves as a reminder that strategic outcomes depend on factors more subtle than firepower and technology. The improvised repairs that Japanese engineers found so bewildering remain visible: wire securing electrical systems, tape reinforcing connections, field expedient patches on structural components. Museum placards explain these repairs as evidence of American pragmatism and maintenance philosophy, though few visitors understand the deeper implications about design assumptions and operational reality. The broader lesson that Yamamoto documented, that equipment designed for maintainability under worst-case conditions outperforms equipment optimized for theoretical performance under ideal conditions, became fundamental principle in post-war military-industrial development. Modern military equipment specifications explicitly require that maintenance be performable by minimally trained personnel using improvised methods. Reliability engineering incorporates assumptions about suboptimal conditions and field-expedient repairs. Training emphasizes practical problem-solving over theoretical knowledge. But the lesson extends beyond military applications to any domain where equipment must function reliably under real-world conditions that violate designed assumptions. Consumer products, industrial machinery, infrastructure systems, all benefit from design philosophy that accommodates human limitations and chaotic reality, rather than assuming expert users and optimal conditions. The wire and tape pragmatism that won World War II reflects principles about resilience, adaptability, and the relationship between design and use that remain relevant across technological domains. The captured B-29 taught Japanese engineers that American success came not from superior technology, but from superior assumptions about how technology would actually be used. Equipment designed for experts requires experts. Equipment designed for scared young people using wire and tape. That equipment keeps working when experts are dead, facilities are destroyed, and supply lines are severed.